Let's start by looking at dividing monomials by monomials. Let's review. When we multiply with exponents, for example, 3 to the 4th times 3 to the 5th, if we write it out or look at it, we get 3 to the 9th, which is 3 to the 4th plus 5th power, or 3 to the 9th power. And if you were going to work that out by hand or hopefully with a calculator, you would find out that's 19,683. So just to review, multiplying with exponents, we add the exponents. And to put it in the most general terms, if we have a base n to the a power times that same base n to the b power, we get n to the a plus b power. And you have to be careful that the base is exactly the same. So our rule for multiplying exponents with the same base is we write the common base, then add the exponents, and if there are coefficients, we multiply those coefficients. Let's turn around now and look at division. We know that it's related to multiplication because division and multiplication are inverse operations. So if we look at division of exponents, we see that 3 to the 4th power times 3 cubed is equal to 2,187. That's equal to 3 to the 4th plus 3rd power, or 3 to the 7th power. Now let's divide 2,187, 3 to the 7th power, by 27, which is 3 cubed, and see what we get. We get 81, which if we break that down is 3 to the 4th power. So we see that 3 to the 7 minus 3 power is equal to 3 to the 4th power. So just as we see we can add exponents for multiplication, it looks like we can subtract exponents to divide. We note that multiplication and division of exponents are inverse operations. If we have x to the 3rd times x to the 4th, that's equal to x to the 7th. If we divide x to the 7th by x to the 3rd, we get x to the 4th. And of course, we can write a rule for dividing exponents with terms of the same base. We write the base and subtract the exponents. We can express it this way mathematically. N to the a power divided by n to the b power is equal to n to the a minus b power. We need to be very careful here to specify that n cannot be 0, because in the system of math we're dealing with at the moment, you cannot divide by 0. It's an undefined operation. It's not clear what it would do. So we say, just don't do it. So if your base, if you have 0 raised to any power, that's still going to be 0. 0 times 0 is 0. But if you're dividing, you cannot divide by 0. Let's look at what happens when you have the same base in the numerator and denominator and the same exponent. For example, suppose you have 3 squared divided by 3 squared. Or with a variable, s to the 6th power divided by s to the 6th power, of course specifying that s is not 0. Let's investigate it. 7 to the 3rd power divided by 7 to the 3rd power is 343 over 343. Whenever you have something divided by the same thing or by itself, you get 1. We see that 7 to the 3 minus 3 by the rule we just had is equal to 7 to the 0, which is equal to 1. Remember we talked earlier and we gave as a rule that when we raised anything to the 0 power, that was equal to 1. Here's where we're going to develop that rule. If we have 3 squared divided by 3 squared, that's 3 to the 2 minus 2 power, or 3 to the 0th power, which is 1. Another way of looking at that is 9 divided by 9 is equal to 1. Here's the rule. Any number or algebraic expression raised to the 0th power is equal to 1, being careful not to include 0. In general, x cubed divided by x cubed, or any base to any power divided by any base to the same power, is equal to, in this case, x to the 3 minus 3, x to the 0. And again, you can see that our variable raised to a power divided by the same thing is 1, or x, the variable to the 0th power, is equal to 1. When you have the same exponential terms in the numerator and denominator, divides out, producing a value of 1. So if you're looking at complicated expressions multiplied or divided, if I have x cubed in a monomial divided by x cubed as part of another monomial, I know that 1 divided by the other will be equivalently 1, and we say it divides out. We can call this cancellation in a way because the term in the top cancels with the similar term you're dividing to give you equivalently 1. And when you multiply something by 1, it doesn't change the value. Let's look at some examples of how this works. Let's take 8a cubed divided by 4a squared. Let's express it this way. The coefficients give me 8 divided by 4. The variables give me a cubed divided by a squared. When I work this out, 8 divided by 4 is 2, and I have a to the 3 minus 2 power, or just 2a to the first power. And you remember, when we have anything to the first power, that's equivalently 1. So my final answer is just 2a. Let's look at another example, a little bit more complicated because there are two variables. I have 12 r squared s to the 5th divided by minus 3 rs squared. Let me cast them this way, where I have the first monomial that I'm dividing on the top, what I'm dividing by on the bottom, and I've separated them out. I have 12 r squared s to the 5th over minus 3 r1 s squared. We can do the math on each part individually. 12 divided by minus 3 is minus 4. R squared minus r squared divided by r to the 1st is r to the 2 minus 1. S to the 5th divided by s squared is s to the 5 minus 2. Going to a new slide to write this out, this gives us minus 4 r to the 1st s cubed, which we can write in the simplest form as minus 4 r s cubed. Let's look at a really interesting example. Minus 55 c to the 7th, d to the 8th, e to the 9th, boy, just saying that, divided by minus 5 c squared d to the 4th. Let's recast it in this form. We have a minus 55 over a minus 5. Now the c terms, c to the 7th over c squared, divided by c squared, d to the 8th divided by d to the 4th, and e to the 9th divided by 1, because there is no e term in the monomial that we're dividing by. Now we do the indicated operations. We have minus 55 over minus 5 is 11, c to the 7 minus 2, d to the 8 minus 4, e to the 9, and if you want to think of it, minus 0, or just e to the 9. And we can work this out. Our answer is 11, c to the 5th, d to the 4th, e to the 9th. Can we get a rule from this? And the answer is yes. To divide monomials with exponents, here are the things we do. We first divide any coefficients. Then for like bases, we write the base and subtract the exponents. Any bases that appear only in one term are just repeated with no change, as we did in the last example. Let's change topics a little bit and use division to find what we're calling a missing factor. I'll show you. If we have 3x squared times something equal to 12x to the fifth, what is that something? In other words, what must we multiply the 3 by to get a 12? And 3 times what is 12? Hopefully your imagination came up with the 4. And what must we multiply the x squared by to get x to the fifth? If you think about that for a second, we need to know that x to the 2 plus 3 is 5, so we need x cubed for this. We found the missing factor. 3x squared times what is equal to 12x to the fifth, so we can put that missing factor we found in here. If a times b is equal to c, and we write this as an equation, we have to do unto one side as you would do unto the other, so we'll divide both sides by a, and we can find the so-called missing factor by using this rule and running it as an algebraic equation. So we find that b is equal to c divided by a. Let's see how this would work with something a little bit more complicated. Minus 10 x squared y squared times what is equal to 20 x to the 7th y to the 10th. We divide both sides of that equation, leaving question mark as the variable, by minus 10 x squared y squared. Then we do the operations that our rule told us to. We divide the coefficients, and then we divide each of the variables. So I have 20 divided by minus 10 times 7 x to the 7th divided by x squared times y to the 10th divided by y squared. When I do the math on this, I find out my question mark, my unknown, is minus 2 from the math, x to the 7 minus 2, y to the 10 minus 2. Simplifying this as much as possible, I find that my unknown factor is minus 2, x to the 5th, y to the 8th. We're going to use this idea in factoring polynomials and looking for something called the greatest common factor. I'll explain what that is shortly. Let's look at some examples. Just to review, if we have 12 divided by 4 is equal to 3, we call the number we're dividing the dividend. We call the number we're dividing by the divisor, and the answer is the quotient. If we're multiplying, we call the numbers we're multiplying the factors in the multiplication, and the result of that the product. We're going to use a process of division to find the factors contained in any product. In other words, we'll have the product, and what I'd like to do, instead of taking the factors to find the product, I'd like to work backwards and see if I can take the product and then find the factors. We divide the product by one factor to get the other factor. It's an inverse operation. 12 divided by 4 is equal to 3. 12 divided by 3 is equal to 4. Let's see how we would do this with polynomials. With polynomials, we've gone in one direction. We've taken two factors and then multiplied them to get the product. And we've used the distributive law to do that if we had a monomial times a binomial or some other polynomial. But this is the product of the multiplication. And remember that we use the distributive law. It becomes very, very important. Now, can we use the distributive law going in the other direction? Suppose we have something, and it might be hard to identify, but there's some common factor in there of, in this case, a. Can we take an expression that's ax plus ay plus az and use it to go in the other direction and separate out the a and express it as a factor of a times a quantity xyz. Anyway, that's what we're going to investigate, looking at the distributive law, but in effect running it backwards. Instead of taking one thing times things separated by pluses and minuses, we're going to take those things separated by pluses and minuses and see if we can pull anything out of it. We're running the distributive law backwards. Let's look at how we do that. We reverse the distributive law. Given a polynomial, ax plus ay plus az, we find its factors, take the a's out, and get something times x plus y plus z. That's what we're looking for. Let's look at an example. Suppose we have 9x cubed plus 6x squared plus 3x. We'd like to rewrite this as 3x times something. And in fact, let's see if we can rewrite it as 3x times the first something, the second something, and the third something. In other words, we're trying to see if we can pull out a 3x from the 9x cubed, pull out a 3x from the 6x squared, and pull out a 3x from the 3x itself. In order to do that, we can divide each one of the terms in that trinomial by 3x, but we come out the same because we've multiplied that whole expression by 3x. If we multiply by 3x and divide by 3x, what we have is 1 times whatever the factor is, so we haven't changed the mathematical value because in each case we're only really multiplying by 1. Then we perform each of those divisions and we find we can have 3x times the quantity 3x squared, because 3x times 3x squared gives me the original 9x cubed. 3x times 2x gives me 6x squared. And 3x times 1 gives me the original 3x. So I've taken a polynomial and factored it, pulled out a quantity that was common to all three of the terms in the trinomial. We call the 3x and the quantity 3x squared plus 2x plus 1 the factors. And in the past, we've called this process factoring. We're going to look at a process that will allow us to factor the biggest possible quantity we can from a polynomial. This factor is called the greatest common factor. We look at each of the terms in the polynomial and try to find something common to each of those terms that we can pull out such that it's the biggest thing possible. Let's look at the procedure for doing it. Here are two things. Think of it as perhaps 24r to the 5th s plus 30r cubed as being a binomial. Let's look at the procedure for pulling out the largest common factor. I break the monomial down into its component parts. Can I take apart 24 into its smallest pieces? If I divide 24 by 2, I get 12. If I divide 12 by 2, I get 6. So there are the two 2's. If I divide 6 by 2, I get 3. So 2 times 2 times 2 times 3 are the smallest things that I can break a 24 into. What about r to the 5th? Well, 5 r's multiplied by each other is about it. And s, there's only one of those. What about the 30? I can break 30 into 2 times 5 times 3, or 2 times 15. Then the 15 can be broken down into 5 times 3. R cubed is r 3 times multiplied. Now we look at both of those and see how many 2's they have in common, how many 5's they have, how many 3's, and so forth. Let's look at that. Here's a 2 here, and that, since there are no more 2's in the 30r cubed term, I'm done with 2's. Here are 2 3's, since there are no more 3's there. On the other hand, there are 3 r's, or r cubed, common to both terms. So I can pull out a greatest common factor of 2 times 3 times r times r times r, or if that were a polynomial, I could pull out a 6r cubed and be sure that that was the biggest thing I could possibly pull out of those two polynomials common to both of them. And that's called the greatest common factor. And the technique I showed you of breaking the thing down to its smallest components and then looking for what's common in those smallest components will ultimately net you the biggest possible thing you can pull out. Let's look at a couple of examples. 70x to the fifth plus 42x cubed plus 98x squared. I see I can pull a 2 times 5 times 7 out of the 70, and I can get an x squared times x cubed. I could even go down smaller than that. But as a trick, let me tell you, I see I have 98x squared. That's the smallest value of x common to all of those. I can pull out a 2 times 3 times 7 from the 42 and x times x squared. And I can pull out a 2 times 7 times 7 from the 98, and there's x squared. I have a 2 in each case. That contributes to my greatest common factor. It looks like I have a 7 in each case. That contributes to my greatest common factor. And it looks like I have an x squared in each case. That contributes to my greatest common factor. So that gives me a 14x squared as the greatest common factor. What do I do with it? I go to the original polynomial and divide all three of the terms in the polynomial by my greatest common factor, and when I do, I find that 70x to the fifth divided by 14x squared gives me 5x cubed. 42x cubed divided by 14x squared gives me 3x, and 98x squared divided by 14x squared, notice I have x squared over x squared, that's 1, gives me a 7. I then multiply that second factor by the greatest common factor, and that's as far as I can go in taking that 70x to the fifth trinomial apart. Here's the rule. To find the factors of a polynomial, we find the greatest common factor for the polynomial, we divide the polynomial by the greatest common factor, and the result, whatever is left, is the second factor for the given polynomial. Let's find the factors of this trinomial. We have, first of all, we see we can pull a 2 out of there. And if we look again, we see we can pull another 2 out because 18, 26, and 12 are also divisible by 2. Let's see what else we can pull out. I see I have a w squared in the first term, a w cubed in the second, and a w fourth in the third. Okay, let me pull out a w squared. Let's look for the common factors in the variables. There is a greatest common factor. Why is that? Well, if I look there, I see there's a w squared. There's nothing bigger than squared that I can pull out, and there's a w in every term. What about x? Let me examine the x's. I see I have x cubed in the first term, x squared in the second, and another x squared in the third, so I at least have an x squared. I can pull that out. What about the y's? I have a y to the fourth, a y cubed, and a y to the fifth. Well, all of those are going to have at least a y cubed in them, so I can pull that out. Then I say, what's left? I take the greatest common factor, the 4w squared x squared y cubed, and divide it by each of the terms in the polynomial to give me that second factor. There it is. Let's try to factor this one. I notice I have a 21, a 35, and a 56. I try to find things that are common to those coefficients. I notice that I can take a 7 out of each of them and get 3a cubed b squared c plus 5a to the fourth c squared plus 8a squared b squared. I look in it next and I try to see what other variables might be common to each one of those three factors. I see in the first one I have an a cubed, the second I have a to the fourth, the third I have a squared. I look at that and I see that I can get at least an a squared out of each of the three of them. I see that's in all of those terms, so I pull that out. Now I go checking. What about b? Well, there's a b here and a b in the third term, but there isn't any b in the second term. So I can't factor a b out because I'm dead in the water. There needs to be a b in that second term for me to pull it out of that expression. What about c's? I see that there are two c's, but there is no c in the third term. So I can't pull a c. There's no c common to all three terms, so I'm stuck here. This is as far as I can go. So my greatest common factor here is 7a squared. We're done. We can't go any further than this.